Okay, so today we are going to look at the tensor product of two modules. We're going to look at the general case of this, the most general, where we're not going to assume that we are working over a commutative ring, which is the way that um, most texts treat the tensor product over commutative rings. We're going to be doing it over an arbitrary ring. To begin, we're going to, in this video, construct an abelian group given two R modules that satisfy a certain universal property. And then in the next video, we will talk about how to give that abelian group R module structure or some S module structure for some ring S. So to begin, to motivate this a little bit, we can look at different ways that we can take two modules and combine them to give us a new module. So as we've written here, given two left modules, M and N, we can form a new left module, new left R module denoted M direct sum N, right? So that symbol, this symbol is the direct sum symbol. Um, and we simply look at the Cartesian product, m cross n, and declare that our addition be done component-wise, and the action of r on m and m times m plus n to be done component-wise as well. And as I said, this is called the direct product. It's actually called the direct sum. Um, but in the finite case, the direct product and the direct sum line up, so um, there's no harm in switching notations. So simply all we're saying is that if we have two components, M1, N1, and M2, N2, we add them component-wise. So that's M1 plus M2, N1 plus N2. And the action of R just is given component-wise as well. We kind of distribute R um, into the uh, into the into the ordered pair. And this, you could check very simply that this defines this condition gives us an abelian group structure, and this condition gives us our left R module structure. Now, if these were right R modules, M and N are right R modules, then the action is just flipped around the other way, and we get another right module. So that's nice. Now, the direct product comes equipped with the natural projections onto its factors. So we denote these pi sub m and pi sub n. And the triple, right? So if we recall, pi sub m, that's going to take a pair, m comma n, and just map it to m. In m and pi sub n, that's going to take a pair and map it to n in n. So we're just projecting onto the first factor, projecting onto the second factor. Now this triple right here, the direct product or the direct sum and the projection mapping satisfy the following universal property. And the universal property is stated kind of abstractly. So for any other triple morphisms, any other triple of R modules, so S is an R module, phi sub m and phi sub n are module homomorphisms from S to M and from S to N, as stated here. There exists a unique R module homomorphism, pi sigma, that's going to map S onto the direct sum such that the following diagram commutes. So this is a nice condition. This is the universal property that is satisfied um, by the direct sum, and this makes it, in the context of categories, this makes it the direct sum construction satisfies the product condition. That's some kind of limit of a diagram and things like that. That's not really that important here. But what is important is that um, whether we can combine two modules to produce a new module, um, ways that we can do this. And you may think that if we look at, so we know that the category of RMOD, they have, well, okay, if we look at the category of, let's say the category of group, we know that the category of group has a product construction that's satisfied by the um, direct product of groups, right? So that's good. But there's also the coproduct construction. There's another one here, coproduct. And in the category of group, um, these are not the same, right? These are not equal. And that's good because now we have another way of combining groups, right? This is satisfied by the free product. Right, so in group, we could look at two different ways to take groups and form a new group out of them that satisfies a certain universal property. This will satisfy the same universal property, not the same one, but it'll be the same diagram, right? So this is the same diagram for the in the category of group where everything now is just a group. So S, M, and N, and M plus N will all be groups, and then this will be stated analogously where all the morphisms are group morphisms. Um, Coproduct will satisfy the dual of this diagram, right? So it'll be the same diagram with all arrows reversed. Um, and that's satisfied by the free product, which we won't talk about today, but it's an interesting construction. So we see in group that we have these two notions of a product and co-product, and they lead to different constructions, or they're different constructions that satisfy these two universal properties. And we can ask this in the category of R modules, right? So we take in the product of two R modules. Is there some other type of product that we can take that will satisfy the co-product universal property? And hopefully it will be different. Um, but this is not the case. The direct sum construction is special in the category of RMOD since it satisfies both the product and the coproduct universal properties. As we just said, we compare this to the category of group where the product is the direct product and the coproduct is satisfied by a construction called the free product, which I just said as well. Um, so the issue here is that the coproduct in RMOD um, is not a new source of ways to combine R modules. There are a couple of ways to attack this. There are a couple of entry points into talking about the tensor product. Um, there's one way, the way that we're going to do it is we're going to kind of finick around, be a little finicky with our universal properties and see if we can kind of tease out some new construction based on a universal property that we're seeking, that we're looking for our new construction to satisfy. Um, that's kind of the way that we're going to do it now. Um, so let's get to it. Um, as I just said, this is basically the same thing we said. So we can play with universal properties. And when we talk about universal properties, we are equally concerned with, if not more concerned with, the morphisms of the diagram and not just the objects that comprise it, right? So in our case of the direct product, right, we are concerned with, yes, that um, these are all R modules, right? So all these guys are R modules, but we are also concerned, we could notice that all of the morphisms are um, R module homomorphisms, right? We can compare that to the universal property for free modules, right? So if we have a set S, um, the free module, which we denote f of S, the free module on the set S, is universal with respect to set maps, right? So um, if we have a set map, we'll call this phi. If we have a set map and we have the canonical injection here, there exists a unique R module homomorphism from the free group, the free module on S into this module M. So this is the universal property that this satisfies. So we have two different flavors of universal properties, kind of. We have the one on the left, this guy right here, where all of the morphisms are just R module homomorphisms, or in the case of groups, they're group homomorphisms. Here, this is a set map, right? So this map may be some kind of other structure, may have other structure, but it's just a set map, and that's the only thing that the universal property is concerned with. So when we're seeking new universal properties, maybe we can relax the conditions. Maybe we can relax the conditions that we require this to be universal to our modular homomorphisms. Maybe there's some other morphism that we can consider. And maybe we can relax the conditions we're requiring to left modules. Maybe we could take, this is hinting at what we're going to do, take a left module and a right module, or yeah, something like that. And we can somehow derive new data, some new data out of combining these things in certain ways. So to start constructing a new R module, we have to first construct an abelian group, which is going to be the focus of today's video. Um, and so as I said, we're going to relax the condition. Maybe instead of taking two left modules, let's see if we can find a way to combine a left module and a right module. So in a sense, and we're going to get a new abelian group out of this. So in a sense, the R module structure, the left and the right module structure kind of annihilate each other, and we're left with an abelian group. On this abelian group, we can add new module structure onto it, provided some conditions are satisfied. But for today's video, we're just going to focus on constructing the abelian group. So as I say here, we're going to start, we're let M be a right R module and N a left R module. This should be 2. So as we've noticed, the direct product of two left modules or right modules is concerned with module homomorphisms. So we can change this condition and ask if there's a new, if there's a module universal with respect to some new type of map. And essentially all we're asking is that we know that our direct product is just the set M cross N. So, you know, M, right, this is just the set M cross N. And when we're looking at, essentially when we're looking at M cross, the direct product of M cross N, we're really looking at, when we want to look at module homomorphisms outside that go out from M cross N. And these are just going to be morphisms of the form phi sub M plus phi sub N. Right, so essentially what we're doing is just taking our, and this comes from the coproduct, since the direct product satisfies both the product and coproduct universal properties, essentially what we're looking at is just pairs of morphisms, where phi m, right, phi m is an R module homomorphism, and phi n is an R module homomorphism. So essentially all we're doing is looking at pairs of morphisms out of the direct product, essentially looking at it factor by factor. Now, this at the root of all of this is we're really looking at maps from M cross N that have certain structure, right? Phi M plus phi N has a certain structure. It's an R module structure, or it has the structure of an R module homomorphism. And we can ask, are there different maps out of M cross N? That's really the root of what we're going to be getting at. Is there a new map out of M cross N that's not an R module homomorphism, but maybe is the next best thing to an R module homomorphism? And it turns out there is, and we've encountered these maps actually a lot. And most maps, almost every time that you do anything in algebra, you're using one of these maps, right? So to motivate the definition, the next definition, we'll let R be a ring, and we're going to consider theta. We're going to consider theta to be the function that denotes multiplication in R. So for example, R1 and R2 in R, we have theta of R1 comma R2 is equal to just the product R1, R2 in R. Um, so we can ask, um, is this an R module homomorphism, or not an R module homomorphism? Is this a ring homomorphism? So if we consider R cross R, right, as the ring direct product of R with itself, which we know exists, and we won't talk about that today, but it exists, and it exists in the same types of fashion under component-wise addition, component-wise multiplication. Um, we can ask if theta is a ring homomorphism from R cross R into R. And it's not. Um, for example, right, if we have a pair, we have two pairs in R cross R, then we can do this evaluation. So theta of the sum is we just add component-wise. Now, this is the key step here. We just do distribution, right? And we do this distribution and we end up with this term. But if we look at it this way, theta of R1 R2 plus theta of R1 prime, R2 prime, we just get this, right? So we see that these are clearly not equal. So theta can't be an R module homomorphism. Um, but theta does satisfy some other properties that are very important. And the properties are kind of motivated from this distribution law here, right? I'm going to list some of the properties that theta satisfies. So if we have, let's say theta of R1 plus R1 prime comma R2, right? So if we look at adding things in the second factor, sorry, in the first factor, that's going to be R1 plus R1 prime times R2, which is going to be equal to R1 R2 plus R1 prime R2. That's going to be theta of R1 R2 plus theta of R1 prime R2. So we see that we have kind of this, it's almost like theta is a homomorphism in the first factor. Right? When we fix the second factor, we can kind of split theta into a sum. So it's almost like a ring homomorphism or some kind of homomorphism, an additive homomorphism in the first factor. And we see similarly, and this is because of distribution on the left, right? So we can distribute on the left. But similarly, we have do the same kind of computation. This is going to be R1 times R2 plus R2 prime. And that's going to be, we distribute again, and we get theta of R1, R2 plus theta of R1, R2 prime. So we have another kind of distribution condition. And so there's another condition that we can talk about. It's we can notice that if we have a product, right, theta of R1 times, let's say, alpha R2, that's going to be equal to R1 alpha R2. And through associativity of multiplication, we can write this as R1 times alpha R2, which is theta of R1 alpha R2. Right, so we see that we have these three conditions that theta satisfies. Um, and it turns out that these kinds of maps actually appear all over the place, and they're crucial to defining the tensor product of modules actually. So this is just the noticing, right? These properties here come from the ring structure of these come from the ring structure. We could see this and this. These are all properties from the ring structure of R, but we can abstract this a little bit to deal with R modules, left and right R modules. So as we said, theta is not a ring homomorphism, so standard ring multiplication is not a ring homomorphism, and we showed that this satisfies a number of other properties, and we're going to state these properties in terms of left and right R modules because this is kind of the most general way that we can express these properties. So we have this definition. So we'll let R be a ring M is a right R module, N is a left R module, and L is an abelian group. So a map phi from the, now here we're just looking at the, we're not looking at the direct product, we're just looking at the Cartesian product. So this has no module structure or even group structure. It's just the product of M and N. So a map phi is called R balanced or R middle linear if the following three conditions hold. So for all M1, M2, and M in M, N1, N2, and N in N, and R in R, we have these three conditions. So we see um, it's it's linear, quote unquote, in the first factor. We have linearity in the second factor, and we have this associativity condition where we can pull the right module structure from M into the left module structure of N. So as I just noted here, MR takes place under the right module structure of M, and Rn takes place under the left module structure of N. So now we have these new maps. As just to recap, we have M cross N, right, which kind of goes into the direct product. Oops, which goes into the direct product. Um, and from the direct product, we have maps out of here that are group or module homomorphisms. But now we also have this other map. We have other maps out of M cross N. These are going to be, so we have some other structure here maybe, and we have other maps, um, and we have other maps out of M cross N. These are R balanced. So we have R balanced maps now. And we can ask is if we have some kind of universal property with respect to our balanced maps. And this is where our definition of the tensor product is going to come in. So for the right R module M and the left R module N, the question in this video is, can we create a new abelian group A that is universal with respect to these R balanced maps? That is, does there exist an R balanced map? So we want an R balanced map from the product, from the Cartesian product into some R module A, I'm sorry, some abelian group A, such that for all abelian groups L and all R balanced maps phi that map the product into L, there exists a unique group homomorphism psi from A to L such that the following diagram commutes. So this is kind of the goal here, right? We're looking at, so these two guys, these are R balanced maps. Right, so we've covered, as we said before, we've covered R module homomorphisms. We have universal properties that cover R module homomorphisms, but we have this other class of maps called R balanced maps, and we want to know if we can construct an abelian group, which we will later turn into an R module or an S module, depending on the ring that we're working over. We can construct a module. This will turn into a module, right? If we construct a module that is universal with respect to these maps. So this is going to be a group homomorphism. And essentially what we're looking at is A is kind of like the best approximation for which we can place our Cartesian product in, such that our balanced maps turn into kind of R linear maps or S linear maps, depending on what structure we're working over. And that's kind of like the flavor of a lot of universal properties is looking for these best approximations for which we can just like the free group, right? This is very analogous to the construction of the free group, um, for which we have a set S and we want to find the most efficient way to embed this set S into a group. where there's no relation um, among the elements of this new group that we're trying to embed our S into. Um, and there's no coincidence that that kind of construction will come up because we're going to extensively use the free group construction. Um, so as we said, our target is to create this abelian group A that satisfies this universal property. Now, the most natural place to start is looking at the FreeZ module on the set M cross N. And we'll denote this by Fz of M cross N. Now, the FreeZ module is just the free abelian group. So this is the best place to start, the most natural place to start, because we want an abelian group that contains M cross N somehow, maybe not injectively, but somehow contains M cross N. This is the place to go. And this is a good place to go because we know that we have a natural injection from M cross N into the FreeZ module. Um, that kind of just sends M and the pair M comma N to itself, essentially, because we know that elements of the FreeZ module are just formal Z linear combinations. So something like this, right? So an element of M cross M would be something like M1, N1 plus 5, M2, N2 plus 7, M4, N4, something like that. Right, so this is just some element of the free Z module. They're just formal linear combinations. Don't mistake these for elements of the direct product, right? Because we can't just add them together because we're looking at that's a different construction, right? Here we're looking at the free Z module. And this is kind of the way that we form free modules for finite sets. Um, yeah, this is kind of a loose example of elements in the in M cross N. There's a more formal argument, but we won't worry about that here. So the FreeZ module comes equipped with this injection, the canonical injection. Um, Now we have this map that we have here. So this map, this is going to be an R-balance map. We're going to take that as given. So we have an R-balance map from M cross N into L, our abelian group. Um, and this gives rise to, by the universal property of free Z modules, or just free modules in general, this gives rise to a new morphism, capital psi, that maps the free Z module into L, such that the diagram commutes, right? So we have psi, I will write with these bars, composed with iota of M comma N, that's going to be equal to psi of M comma N, which is going to be equal to phi of M comma N. So that's how we define it, and then we extend it linearly, right? So we know that elements here are these formal linear combinations. So we have psi of the sum of M comma N, M sub I, N sub I, maybe this is R sub I. That's going to be equal to the sum of R sub I, phi of M sub I, comma N sub I. So we just kind of extend this function linearly, and that gives us the desired homomorphism. And it's a good exercise to check that this is uniquely defined. I think it's clear that it's unique because it's forced by the diagram, um, and it satisfies this universal property. Yeah, so this is good, right? So this is a good place to start because now we have this is R balanced. Iota is not R balanced. Iota is a set map, right? So that's what I note here. So we know that phi has additional structure. If we take into account that M and N are right and left R modules, as we said, we know phi is R balanced by assumption. So we want to somehow upgrade iota to be R balanced while still keeping the unique group homomorphism phi. psi, because if we do that, then we've satisfied the universal property, right? So if we somehow make this guy R-balanced, if we make iota R-balanced, and we can maintain this unique group homomorphism, then we've satisfied this universal property. But of course, it's not that simple, because iota is not R-balanced. Iota is the canonical injection. It's just it's a set map. Because we're looking at this with no structure. So to force iota to be R-balanced, we have to modify the target group in a very specific way in order to achieve it won't be iota anymore, but it will be a I was going to say derivative, but that's not correct. It's going to be related to iota. So we have to define we have to quotient out by the relations that we defined in our first definition. And when you first see this, it may seem obscure, but if we stick around for a little while, we'll see that if we consider the subgroup generated by these relations, H, right? So I just take these brackets to mean the subgroup generated by these elements. And then we know this is a normal subgroup, right? Because the FreeZ module, the free abelian group on M cross N is naturally, it's abelian, right? So H is a normal subgroup because every subgroup of an abelian group is normal. So we don't have any problems there. So as I've noted here, the standard operation in the quotient is well defined. So we have a quotient group, which is FZ of M cross N mod H. Now you get a new diagram, right? We have this new diagram. We have the original iota and M cross N. Then we have the canonical projection, right, which takes an element and maps to its coset. So we have this natural projection that sends an element of the free group onto its image in the quotient, so that exists for any kind of quotient object, and then through composition. So this is going to be pi composed with iota. Through composition, this turns into a map from the M cross N into this quotient. And now, with this setup, so we claim that iota prime is now is an R-balanced map, and we could just do a simple check. So if we're given two elements of M and an element in N, we have our additivity. So iota prime of M1 plus M2 comma N. That's going to be pi composed with iota of M1 plus M2 comma N. And then we just go through the simple check. Yeah, and we get that this, and we have this expression here, and these are equal, right? We know that they're equal because in the quotient we have that M1 plus M2, right? This is one of the elements of the generators of H, right? So this is in H. Or I'm sorry. This is in H, right? So we know that that's set to 0, which gives us that M1 plus M2 comma N plus H is equal to M1 N plus H plus M2 N plus H, right? So we see that these two expressions, these are equal, which gives us the fact that iota prime is R-balanced. And we can perform similar calculations to show that we have that it is linear in the second factor, and we have the associativity condition with our multiplication. So let's take stock of what we have. Um, the following diagram sums up all of the groups and morphisms that we have already created, right? So in the first triangle here, this one that I'm highlighting in white, um, this commutative triangle, right? This comes from the free group construction, right? We're given the map phi from M cross N to L, um, and the free group, right? This factors uniquely through the this factors uniquely through the map psi, so that's good. And then this second triangle, which I will highlight in green, this second triangle here, this second triangle, this comes from the quotient construction that we just performed. So we passed the free group, we modded out by this special subgroup H, and then we obtained a new map I prime, which I'm calling I now, I prime, um, that maps that's composition with pi from pi and I, which we called iota in the previous slide. I meant to call them iota, but I accidentally called them I. Um, so we have these two triangles, and what we really want is we want a map from this new free group object. It's not a free group anymore, but this quotient of the free group into L, because then we'd have this triangle here would be commutative, where this is R balanced and this is R balanced. So that's kind of what we want. So we kind of, what we want to do is we want to find a way uh, to move psi to become a map from the quotient of the free group to L. And then that would imply that the free group Fz of M cross N mod H, that satisfies the universal property that we are looking for. So the question is there a way to push psi out to a map from the quotient into L? It turns out that there actually is a way to do that. If we look at the leftmost triangle, right, so this is going to be, looking at this triangle here, we know that this composition, psi composed with I, is equal to phi of M comma N, right? And we know this from the fact that just from it being commutative, it's forced to be commutative, and we take it and extend it linearly, as we said in a previous slide. We simply extend phi linearly to all sums. Just let's write this down again. So we know that psi of M comma N, it should be psi of iota of M comma N, which is equal to psi of M comma N. That has to be equal to phi of M comma N. And then we extend it linearly. So we have psi of, because we can have sums in the free group. So the sum of R sub I, M sub I, N sub I is equal to phi, is equal to the sum of R sub I, phi of M sub I, N sub I. So we just extended linearly just to the sum. Um, so I point that out here. So on the elements of M cross N, this is what we have. And since phi's are balanced, psi maps the generators of the subgroup H to 0. Okay, how can we see that? Well, we can see this as follows. We have psi of, let's take a generator, right? So this is an element of H, and we can split this element up because psi is a is a homomorphism, is an R module homomorphism. It's a group homomorphism in this case, but it's an R module homomorphism in the general case. When we consider L as an R module, or we consider L as a Z module, right? Because it's an abelian group, so it actually is a Z module. But we can split it up, and then we rewrite it in terms of what we had above. And then we see that because phi is R-balanced, we can write this splits up in the first factor, and that of course is equal to 0. And this holds for all of the generators of H. So a similar check shows the generators get sent to 0, and from this we can conclude that H is a subset of the kernel. Okay, and this is important because if we look at the rightmost triangle, right, so if we look at this triangle here, if we look at this triangle, we know that um, since H is a subset of the kernel, um, we have a standard setup for the fundamental homomorphism theorem. So there exists a unique homomorphism, psi prime, from this quotient to L, such that the following diagram commutes. Okay, and this is just the standard homomorphism setup, fundamental theorem of homomorphisms, and we define psi prime, right? So that takes an element um, of our coset. No, I'm sorry, this takes an element of our quotient, and it sends it to psi of m comma n. And now, of course, here we define this. I'm defining this just on the kind of simple elements, but of course, an element here, right? An element here is something of the form r sub I, m sub I, n sub I, right? And we projecting this into its quotient, this would be something of the form r sub I, m sub I, n sub I, plus h, right? So these are the cosets. Um, Here I'm just writing it in the form of just single elements, right? Because of course we have mn here, and that gets sent to mn plus h. I should have included a sum here, but it doesn't hurt to just write it this way, because what we're most interested in is this bottom triangle. So what we're most interested in is this triangle here, and now we have this new map psi prime. Now we have this new map psi prime, and we want to know if this diagram commutes, because if this diagram commutes, then our quotient object here satisfies the universal property that we are looking for. Um, we know that psi prime is unique because this fundamental theorem of homomorphisms guarantees that psi prime is unique, and we know it exists, so we just have to show the diagram commutes. Now, to show that the diagram commutes, we look at psi prime composed with iota prime. That's going to be psi prime of, now we know that iota prime, right, that iota prime is the composition, right, so this sends mn to mn, that sends it to mn plus h, right, so the composition, and we know that psi prime of mn plus h is just psi of m comma n, and we know that that's equal to phi of mn. And as I said here, we use the fact that iota prime is this composition, that psi prime of m comma n plus h is psi, capital Psi of mn, and by the fundamental homomorphism theorem, and we use the fact that psi of mn is equal to phi of mn by the universal property of free modules. So we've used all these universal properties, and we've shown that the diagram commutes. Now, this is where the notation comes in, because we've done the hard part. We denote this element, this object here, we call it the tensor product, and we call it m tensored over r with n, um, and we represent the coset of m comma n in h, the coset of m comma n plus h, of m comma n in the tensor product as just m tensored with n, and that's how we say it. We say m tensored with n. And from this construction, um, from the construction of H, right? So from the relations in H, we can conclude these. That just comes directly from the definition of the elements that generate H getting mapped to 0, and we have these linearity conditions. And we have also proven that this tensor product satisfies the following universal property. So we let R be a ring with unity, and we let M and N be right and left R modules respectively. We denote now by iota that maps M cross N into M tensored over R with N. The R balanced map that is defined by sending M comma N to its coset, which is we're denoting with this tensor symbol, M tensored with N. We know that that's an R balanced map as we've shown before. Then for all R balanced maps, phi from M cross N to L to any abelian group, there exists a group homomorphism, M tensored with R, M tensored over R with N into L such that the following diagram commutes. So this is the same as this diagram, except we're just relabeling things, right? So now this is M tensored over R with N. This is our same L. This we're calling iota. What are we calling this? This we're just calling psi. So we relabeled some things, but we've shown that this is the universal property that the tensor product satisfies. So just to recap, we look at M cross N. We look concerned with R balanced maps coming out of M cross N. We look at the free group generated by M cross N, the free abelian group generated by N cross N. We quotient out by the set of relations to create an R-balanced map out of M cross N. And this R-balanced map, so this R-balanced map and the tensor product, right? So this triple here satisfies this universal property, such that for all R-balanced maps out of M cross N, they all factor through uniquely. They all factor uniquely through the tensor product. So the tensor product is universal with respect to R-balanced maps. Now, in the next video, we'll turn the tensor product from an abelian group into a module over some ring, and that will require M to be something called a bimodule, and we'll tackle that in the next video.